Good day. So in this video, I'm going to show you a couple of examples on single variable optimization. So as you've seen in your lecture slides, optimization is one of the key tasks involved in economic analysis. We're not just looking after the direction of the function with respect to its independent variables, with respect to the signs. We're also interested in what values of your domain or your values of x will maximize or minimize, or in a general sense, optimize your objective function. So in economics, we're using optimization in a rather simplistic manner, in the sense that we don't need to really examine the characteristics of the functions anymore in order to ascertain that the candidate solution for optimality is indeed a global solution, or global optima, so to speak, because we've been using a lot of assumptions. We're putting assumptions in place to ensure that the functions, our objective functions, are well behaved, in the sense that we only need to use the first order conditions to know that the candidate solution is indeed the optimal solution. So for the next couple of minutes, I'm just going to show you some examples involving profit maximization, cost minimization, or your typical exercises in economic theory that you will most likely encounter in your higher level courses in this program. So for example, let's say we are looking at a production function. Now, single variable optimization, unconstrained in this case, are typically seen in the areas of profit. It's typically used in maximizing profits because you're just selecting inputs. Basically, in profit maximization, you're just selecting inputs without any constraints, no? Without any constraints on the amount of inputs that you can use. Right. Of course, that will change later on when you talk about utility maximization. Consumers maximizing consumers' utility because the consumer is bound to consume only within his or her budget constraint. So let's look at the firm. Let's look at the case of a single firm that utilizes only a single input. This is a simple uh, rather simple example of how to do um, single variable optimization. So the rest of the nuances of optimization, especially for arbitrary or generic functions. It can be found in the lecture slides already. So let me just look at this example of a firm that is said to produce quantity of with the production function Q squared of L, right? L is of course the amount of labor employed, and let's say that the price of the commodity, the selling price, is set at 160, right? And let's say that the wage rate is set at 40. Let's see, that's wage is set at 40. Now, how would you construct the objective of this firm, right? So in this scenario, the firm is choosing the level of inputs, right? He is choosing the level of inputs that will supposedly maximize his profit. So the objective function should be the firm's profit. This is typically noted as pi. So that's going to be 160 Q, right? This will be his revenue, right? Minus minus the cost of employing labor, and that will be 40. That's wage, right? Times the number of units, of L that he employs, right? But of course, you know what Q is. So Q here is basically pi. So the firm wants to maximize uh, pi, which is equal to 160 times 2. So that's going to be 320 square root of L, L minus 40 L, right? So that would be the firm's objective function, right? What will be that L? What will be that labor? What would be the amount of labor that will maximize the firm's profits. All right. Now, let's just say that assumptions about the profit function and the production functions are already in place. So all we need to do is look for the what we call the first order conditions. Of course, you can verify this later on using second order conditions, or if you're looking at the shape of the, if you look at the shape of the profit function, right, you will see that you will see later on that you can verify further that whatever amount of L that we choose here will be indeed the global optimum, right? And you'll, of course, you just have to refer to the slides. You'll have to differentiate local optimum from global optimum, because our objective here is to find the global optimum, not just the local optimum, which means that it should be the maximum for the entire function and not for just a subset of points within the function. Right. So to get the first order condition, we'll need to get the critical points for the function. That is, what will be the points, what will be the points within the function that will set the derivative equal to 0, right? Or there will be no increase nor decrease. There will be no increasing nor decreasing, right? With respect to L. So that would be given by the derivative of pi with respect to the derivative of L, right? So that's going to be 160. Let's just say this is L raised to negative 1/2, right? Because that's going to be 1/2 minus 1, so negative 1/2. That's 160 because, of course, 1/2, so 320 times 320 times 1/2, or 320 divided by 2, that's 160. And you'll have here the constant 40, and you'll just have to equate it equal to 0. So that will be the first order condition. First order necessary condition for optimization states that if L is an optimum, right? If L star is indeed an optimum, then the derivative, or the value of the derivative of the function, right? When you plug in L star in the derivative of the function of the profit function, it should be equal to 0. Right? It's you can again check that in the slide. So here we just need to solve for L, right? Just need to solve for L to get the value of labor, the amount of labor that will maximize the firm's profit. Okay. So let's use another slide. So that's going to be 160. Let me just copy this. We'll have 160 L raised to 1/2 minus 40 equals 0. So you can just move 40 on the other side. So that's going to be 160 L raised to negative 1/2 equals 40. Okay. You can actually divide both sides by 40, and you'll get 4 L raised to negative 1/2, and then that's just equal to 1, right? 40 times 4, 160, right, equal to 1. So moving L raised to 1/2 on the other side, you'll just get L raised to 1/2, or square root of L basically, equals 4, and therefore the optimal, assuming of course everything is in place, the optimal amount of labor, L star, that will maximize the firm's profit would be, this is equal to 4. Optimal amount of labor would be equal to 2, all right? So the firm should hire, basically the firm should hire 2 workers, given the price of input 40, and given the market price of 160. Hiring more than that will eat up on the firm's revenue and will yield lower profits. So that would be your optimal amount of labor. Now, in economic theory, usually you will see rather you will see a rather general functional form for profit maximization. So normally you would see something like this. So suppose you have a production function f of L, right? And don't worry, that's perfectly fine. Right? Suppose you have this production function, right? And let's assume that the derivative first derivative of the production function is positive, right? And the second derivative is negative. What does this mean? It means that your production function is increasing at a decreasing rate. And this basically invokes your diminishing marginal product. As you hire more workers, the additional or the contribution to the total output diminishes. Right? The contribution of the last worker diminishes as labor increases. Right. So let's suppose that P is equal to 1. Right. Let's suppose that P is equal to 1 and your input W would be your wage. Right. So no numerical value for wage. Right. So the question is, what would be the first order condition for maximizing profits? What's the first order condition for maximizing profits at L equals L star? So it's simply you just need to construct, basically you just need to construct the firm's profit function. So that's gonna be, of course, another thing here. You have max. You're choosing L, right? Maximize the profit function such that you assume that the price is equal to 1. So you just have F L, right? Because price is equal to 1, right? So FL minus WL. Okay. So the first order condition would be d pi over dl, right? So that's going to be f prime of L because you just take the derivative of the function with respect to L, right? Minus W equals 0. All right. So therefore, without any functional form, we're just saying that the first order condition, let me just type it here, FOC, the first order condition states that we should choose L such that it must, right? You choose L, basically choose L such that it equates the marginal product of labor with respect to the input price. Now, in a more generic sense, if we didn't assume that price is equal to 1, then that should be something like the marginal product of labor should be equal to the real wage rate because you're gonna divide W by P. So that's your first order condition. That's the criteria that will maximize. That's the selection criteria that will maximize the firm's profit. Right? You'll have to choose labor such that it equates marginal product and wage rates. Right? Now, let's have another interesting question here. So let's suppose, well, of course, we already know. Let me just copy this. We already know that this is the optimal condition, and definitely you'll be obtaining L star, right? You'll be obtaining L star here, right? You'll be obtaining L star from this marginal product, and definitely the solution will normally look like the solution will normally look like another function, right? That's going to be a function of W. Right? This is going to be a function of W. Okay. Now, if I plug this L back in this condition, we'll have a composite function, right? We have a sort of a composite function of W, and that's equal to W. Now, the next question is, how will this optimal labor change, right, when wage rates increase, right? How will optimal labor increase when how will optimal labor L star change when, say, wage rates change, right? So it's just a matter of taking the derivative or the total derivative of this entire expression. So that's gonna be F double prime, right? L star. I'm gonna leave out the expression, and we'll have an expression for dl star over dw, right, by chain rule, right? So that's gonna be dl star over, oops, it's not supposed to be that, right? So dl star over dw, right? And that's equal to 1, okay? Now, we're interested in this. The question was, how will L star change with respect to W? So this is already your answer. It's just a matter of moving. It's just a matter of moving all of the other terms in the right-hand side. So DL and signing, of course, the entire expression. Right? So that's DL star over dW, and that's equal to 1 over F double prime L star. Right? And what's the sign? We have seen earlier in the assumption that you have seen earlier in our assumption that f double prime of L is negative. So therefore, if the denominator is negative, this entire expression is practically negative. And intuitively, what does it tell us? It means that after you select your optimal level of labor, right, that will maximize your profit, holding everything else constant, if wages increase, right? If wages increase, it means that your labor becomes more expensive, and intuitively you will be hiring you'll be hiring fewer workers because the workers or your labor becomes more expensive, hence the negative sign here. So holding everything else constant, an increase in wage rates will diminish or will reduce the amount of labor that you will be employing, right? So that makes perfect sense, of course. Right. So that's one example. That's one example involving perfectly competitive markets, and we're using single variable unconstrained optimization to present the case for perfectly competitive markets. Now, let's have another example involving non-competitive markets, and this is typical. You will encounter this most likely in your micro 2, right? For imperfectly competitive markets, right? So alternative market structures that are not with firms or who are not price takers. Right? Let's look at the case of a monopoly, right? So suppose you have the demand function. Now, in the case of a monopoly, the firm is facing the entire demand function because he's the sole firm that provides or that sells in this market, right? So suppose that the demand function, right? Demand function is given by PQ, A minus Q, right? In the perfectly competitive markets, the firm doesn't worry about the entire demand function. He only takes price. The firm, among all of the many firms in the competitive market, he only takes P as a given. Right? So it's something like given that's something fixed. No? But in a monopoly, since there's only one producer, he cares about this entire demand function because this will determine when he sets Q. This will sort of change the price, and of course, this will have an impact on his total revenue, and it will have an impact on his profits, right? So this is A minus Q. Let's assume that K, right? Let's assume that you have a parameter K, that is between 0 and 1. Oh, by the way, this K refers to the average cost, right? Or the unit cost, right? This is your unit cost of producing Q, right? Normally, this will simplifies this sort of simplifies things. No, if you have a unit cost that's a constant, it also implies that your marginal cost is constant, right? So, what would be the profit function of this firm? So, the objective function for the monopoly. Let's mark this as your monopoly case. So, your monopoly case. Right? So the objective function of the firm would be something like he needs now to choose not inputs, no, as typical in understanding or in analyzing the case of the monopoly. So you just have your demand function, which is your price basically, your inverse demand function times Q minus KQ. Right? So that would be the objective function. Very simple, right? So we'll just have to plug in what Q is, right? What's that Q, right? What's that Q? So this is going to be equal to A minus Q times Q. This is your revenue, and this will be your cost, right? Revenue and cost. So this is where the condition MR equals MC comes from, right? Your marginal revenue must equal the marginal cost. So marginal revenue equating the marginal cost comes from the FOC, right? Comes from the FOC. Why? Because if you take the FOC of this profit function, right, if you take the FOC of this profit function, you will see something like the derivative of pi respect to dq, right? That's going to be equal to the derivative of the revenue, right? And if you take the derivative of something, we attach the term marginal, right? So that this becomes your marginal revenue, right? So this is going to be, and using the product rule, you have two functions here, and you need to use product rule, right? So you have A minus Q plus, or actually it's going to be minus, no? Right? Let me put some brackets here. This actually becomes a minus, right? So you take the derivative of this inner function, A minus Q, right? Minus, right? Q, right? A minus Q, right? A minus Q minus Q, right? Or if you want, you can just distribute this Q within this bracket and you'll still get the same results. Right? So this bracket term is basically your marginal revenue, right? It's your marginal revenue. And this is your marginal cost, right? This is your total cost function. You take the derivative of the cost function with respect to Q, and you just end up with the small k equals 0, right? And let me copy this entire expression, right? It's the monopoly. Right? So you have A minus 2Q, not surprising, A minus 2Q equals K, right? And we'll just now have to solve for Q star. So Q star will be equal to A plus A minus K, A minus K, oops, A minus K over 2. Right? So moving terms, so you have A minus K, you have 2Q on the right-hand side, divide both sides by 2, and you'll have the optimal quantity. You'll have the optimal quantity for this monopolist. Now, next question. This quantity, now that we know this quantity already, how will the how does the monopoly profit then react? So the next question is, how does monopoly profit react to changes in, say, in K? Copy this question on the new slide. How does a monopoly profit react to changes in K? It's simple. Just have to look back at the profit. Just have to look back at the profit function and plug your optimal solution in the profit function. So that's going to be PQ star times Q star minus KQ star. Okay. Simple as that. Okay. So we just have to take the derivative again. No? We just have to take the derivative of this entire profit function, with respect to k, right? Well, but of course we know that q is now a function of k, right? So in simple terms, or we can just derive the formula from here and just plug in the expressions later on, right? So that's going to be d pi of q star with respect to dk. So we'll need to get the derivative. We need to get the derivative of this expression, right? Or you can just make it a little simpler. No? Just distribute q already. So you have a, or well, let's distribute it here. So that's going to be a minus. That's going to be a q star minus q star. How do you do this? Q star squared, right? Because this, right? Because of this, right? Q star squared minus k, sorry, kq star. So you take the derivative of the profit function with respect to k, so that's going to be a dq, a dq star over dk minus 2q star 2q star dq star over dk, okay, minus this will require the product rule. So this is going to be q star. Okay, let's put a bracket here. Q star plus k dq star over dq star over dk. Right. Now we'll just have to plug in dq star over dk. So dq, the derivative of q star with respect to dk is equal to, well, look at this expression. So this is practically a minus 2, k minus 2. So that's just going to be negative a over 2 minus k over 2, right? A over 2 just disappears and you're left with negative k over 2. Take the derivative with respect to k. That's negative 1/2. Negative 1/2. Okay. So I plug it here. Just have to plug it in, right? So you'll have d by q star over dk equals, right, equals a over 2, negative a over 2, negative a over 2 plus well, 2 disappears, right? Plus q star minus q star. Right? Q star will basically disappear, positive, minus, plus or basically minus k over 2. Or plus, sorry, this is going to be plus because minus minus minus, but this becomes this is also negative, so this could be plus k over 2. Q star minus q star will disappear, and therefore the derivative of the profit function with respect to k will be a k minus a. Right? It's going to be k minus a over 2. Sorry, just looking back at the assumption, so this should be a. Right? Now, since k is less than a, intuitively, this will be negative. Right? And what does this mean? It means that as the cost, as the unit cost of production increases, right, and that's denoted by k, your profit will also diminish, as given by this negative sign. So mathematically, it gives us this proposition, and intuitively, it tells us that it's correct because when the unit cost of producing Q increases, it becomes more expensive for you to uh, really it's going to be more expensive for you to produce q, and that of course will have an effect on your revenues, that will have an effect on your profits. So it will diminish your profit when the cost of production increases. So makes sense. That should make sense. So aside from obtaining, as you have noticed, aside from obtaining the optimum quantities, optimum values for our objective functions, we're also interested in how how the optimal values behave with respect to changes in some of the parameters. And that will be the usual. That's going to be the usual exercise in economic theory. Right? We're not just interested in finding the optimal values of these objective functions. We're also interested in how these functions will behave. Right? That's part of basically it's all part of the what we call comparative statics in economic theory. Okay. Probably let's have one last example. Now let's consider this model. Let's consider this hypothetical economic model. Everything is hypothetical anyway. So let's suppose you have this economic model that shows you the proportion of families, right, whose income is no more than X and who has a home computer is given by. So this is a proportion that's going to be P of X, right, given by A plus K 1 minus E raised to negative CX. Right? So that's your proportion, right? Where we assume A, K, and C are all positive constants. So we want to just determine, right? Just determine P prime of X and P double prime of X. Right? That's it, right? And let's just determine whether this function has a maximum, if this proportion has a maximum. So taking the derivative of the proportion with respect to X, right? We'll have, right? A will disappear, so you have and K of course will also disappear. So you have K, right? Negative KC. Right? You have negative KC. Or actually, it's gonna be positive, no? Because of the negative C. We're gonna have some positive KC E raised to negative CX. Right. And then we'll have d double prime. You have the second derivative of px with respect to dx squared, right? And then you have you take the derivative of this function, no, with respect to x, right? So you'll have negative kc squared e raised to negative cx. Now the thing is, if we use the first order condition, for this expression, right, we'll get something. We'll get some weird answers, or not really weird. It's just that we cannot use. Just make us conclude that we cannot use a first order condition to um, determine the optimal condition for cx, because as you noticed, right, this is basically equal to, let me just copy this. If we set this equal to 0, it doesn't really make sense because there is no value. Basically, there's no value of x. Right? There's no value x such that there's no value for x. There's no value x that will satisfy this condition. Right? They set this equal to 0. K and C are positive constants, right? And E is always positive. So even if you set E to 0, right? Even if you set x, or even if you set x to 0, you'll just get another positive number which is equal to 1. So there's no x. There's no x that can satisfy this FOC, right? Of course, you cannot use the first order condition to determine the maximum. No? You can use the first order condition to determine the maximum of this expression. Possibly the next solution that you can do, right? Next possible solution that you can do is you can plot this diagram. You can plot this diagram and then show whether the function has a maximum or a minimum. So you can assign arbitrary values for k, for c, and for a, and check whether there's an optimum, if you can obtain the optimum value for the function graphically. But as it is, using the first order condition doesn't cut it. You cannot use the first order condition because this is not possible. This is not possible. That's not possible. There's no value, there's no x that will satisfy. There's no x that will satisfy this first order condition. Right, so in the next video, we're going to talk about multivariable optimization, right? And then we'll slip right in some examples of constrained optimization, which is typical in consumer theory. Again, any questions regarding this video may be addressed or may be posted in our discussion threads, in discussion groups.